Hey everybody, and welcome to your first algebra PowerPoint presentation. So I just want to quickly talk about what we're going to be doing for this unit. We're going to be talking about waves and wave mathematics, which is called trigonometry. So we're going to be looking at that whole study and then looking at earthquakes and how wave math can be applied to real life situations. Okay. So we start with waves in real life. So there are a few different kinds of waves that exist in real life. The first is sound. So when we hear things, they can be represented as waves. Sound like transmits and passes through the world as energy in waves. Okay. So if you were to watch, look at really anything, look at your iTunes, your iPod. Sometimes when you're looking at the bar as it's playing, like it moves up and down. Or if you're looking at like any kind of audio software, it always represents audio kind of like that. Light is another one. So visible light, colors, and all of that kind of stuff, that is actually represented as waves. It transmits through the air in that wavy form. Ocean waves, right? Like as oceans, I mean, they're called waves, but the movement back and forth of waves and how they kind of crest and fall, that's waves. And then seismic waves, which are like earthquakes, waves through the ground. They kind of go up and down, just like waves. So to understand how waves work, we need to look at how often they repeat, how long they are, that is the wavelength or period, how long they last, their vertical size, so how high they go. And to predict that behavior, we actually use a mathematical formula. It's sort of a one size fits all. Once you understand how to look at wave behavior through a mathematical formula, it applies to all types of waves in real life. So a wave's shape repeats over itself in a consistent interval of time and distance. So when you draw it, it looks like a circle, but if we then stretch it out, look at how the top half of the circle is here, and then we literally take the bottom half and we sort of just shift it over so that it goes up and then down, and this is the bottom half of the circle. It's just flipped the other way, okay? So that's essentially a wave. It's a circle split in half and then moved so it goes up and then down. So we use the same term trigonometry. You might have heard it used in reference to a triangle. That is because trig, means like triangle, tri, three sides, that whole thing, right? Trigonometry is really the study of triangles, but there's a reason why we use a triangle to talk about wave shape. And it has to do with this triangle setup right here, where like if you have studied this in algebra, basically it's SOHCAHTOA, if you may have heard it that way. It's sine opposite hypotenuse. So sine equals the opposite over the hypotenuse, cosine, which is adjacent over hypotenuse, and then tangent, which is opposite adjacent. So SOHCAHTOA, SOHCAH, and TOA. It's like a short form to help remember the sine, cosine, tangent rules. So when we're looking at angle A, the opposite is directly opposite from the A. The hypotenuse is the longest side, obviously, and then the adjacent is the one that's right next to the angle. Now, we're using these same names because the terms sine and cosine and tangent initially came from triangles. Like they came from the study of triangles, but we use those same terms because it works in the same way when we're dealing with the waveforms. So how does trigonometric ratios, the sine, cosine, tangent stuff, connect to wave functions? Well, what we do is we basically take that triangle and we place it in a graph and then put a circle over that, okay? This is what we call the unit circle. The radius of this circle is equal to 1, okay? And the way we measure that is we start from the origin and we go to the edge of the circle. The length of that is equal to 1. Now notice the line I'm drawing right here with my arrow is the same thing as the hypotenuse. The hypotenuse and the radius are basically the same thing. They have the same value in a unit circle. The angle right here is A. It's the angle that's formed between the line of the hypotenuse and the x-axis, and that is the angle A, which we're going to talk about in reference. Again, the opposite is directly across from that angle, and the adjacent is right next to it. Now, notice how the adjacent is on the x-axis, okay? And then the opposite is a vertical thing. It's parallel to the y-axis, okay? So basically, the legs, the opposite and the adjacent, they have become the opposite and adjacent values. And the opposite corresponds to the y. So this xy coordinate, this point on the circle, corresponds to the value of the adjacent and the opposite, because the adjacent value, this x, is the same length as this part right here, right? You know, going from this x to the y-axis, from 0 to whatever this is. So x is equal to the adjacent leg, and opposite is equal to the y, okay? So that's how we get the values of x comma y. We measure this angle in degrees or radians. Radians is like it's an amount of the angle, like it's a measurement of the angle in terms of pi. Don't worry about it. I'm not going to go into too much detail, but if you happen to study that in school, then that's there for you. So we represent the shape of a wave using the sine function. Y equals sine of x, okay? And literally that's all you have to understand. It's like this information, the whole sine, cosine, tangent thing comes from the triangle relationships. But in terms of what you're going to have to do in this class and in this unit, you don't have to do any of that crazy stuff. Like you don't have to prove it or do any of that. Just understand that it comes from that, okay? And this is the equation that we're going to be dealing with, y equals sine of x. This describes how a wave should be plotted on a graph, okay? Sine graphs always start at the origin, at where the x and the y meet, at the values of 0, 0, okay? This right here represents a full wave because it starts at 0, 0, it goes up, and then it goes back to the x-axis, and then it goes down, and then it comes back to the x-axis, okay? So basically, if we were to pick up the bottom half of this wave and we were to attach it to the top half, it would sort of make a circle, okay? And that's the idea. Once it fully makes a circle, and it goes fully up and fully down, and it comes back to the x-axis, it is that's a full and complete wave. Now, waves and the cosine and the tangent values. You really just have to know that this is what tangent looks like, okay? Basically, it sort of looks like it goes from top right to the bottom left, and it sort of looks like just like a weird squiggle, okay? Like a whoop, and that's it. That's all you have to know. Like, I'm not going to test you or like put in the project like how to do this part. This is just for your information. Cosine, however, you are going to have to know. And really the only difference between a cosine and a sine wave is that the cosine wave starts on the y-axis above the origin, okay? It starts at the amplitude, which we're going to talk about next week. But basically know that it starts on the y-axis above the origin. It's not at 0, 0, it's somewhere else, okay? Anywhere else, but just not at 0, 0, okay? And that's where a cosine equation starts from. All right, and I believe that is it for our PowerPoint today. So what you're going to do is you're going to do an exercise just identifying sine and cosine values, and you're going to practice doing that, answering some questions, and then I will see you next week for a conversation about what amplitude and period are and how to calculate the wavelength and stuff. Okay, thanks guys, bye.